Students, very good afternoon. This is Mayur S. More, your chemistry tutor. I welcome you all to JEE Chemistry session number 9 for a chapter called Structure of Atom. Now we have started this chapter. We have already covered the 8 sessions for it. Okay. And now today we're going to see the ninth session of it. Okay. We had seen the dual nature of matter. We had seen the quantum numbers and we have seen everything that we have in the structure of atom. And okay, and today we're gonna see photoelectric effect and the types of nodes. Okay, so very good afternoon. I welcome you all to JEE Chemistry session number 9. Let's begin. So, photoelectric effect. What is photoelectric effect? See, when a light, see what is mean by photoelectric effect? You can understand from the name itself. For the main factor here. See, when a light of certain frequency, strikes the surface of metal, when the light of certain frequency strikes the surface of metal, electrons are ejected from the metal. Electrons are ejected from the metal. See, this is eject some of the electrons. It ejects some of the electron, and this phenomenon is called as photoelectric effect. Okay, those ejected electrons are called as photoelectrons. So these electrons that you are seeing here are called as photoelectrons. These are your photoelectrons. So any metal when it is strike with certain frequency, it will eject the electrons, and that phenomenon is called as photoelectric effect, and those ejected electrons are called as photoelectrons. Okay. Very few metal which are having low ionization energy. What is ionization energy first? See, whenever your metal is like this, okay, you need to convert that metal to gaseous state. When it goes to gaseous state, you start heating it, and that heat energy is not equal to your ionization energy. Then your metal loses the electron to give you Mg plus E minus. It is called as ionization energy. What is the definition of ionization energy? It is the energy required to remove. The valence shell electron of an isolated gaseous atom or ion. The energy required to remove the last shell electron. That means valence shell electron. You already know what it means by valence shell. Right? To size of your metal. Why? Because see, this is your metal. This is nucleus. This is its valence shell. See, this distance is quite less now, right? This distance is quite less. Electron is here. And if you consider another metal which is large in size, so this gap between nucleus and electron is large now. So this D2 and this is D1. Your D2 is larger than D1. So when your D2 is larger than D1, what happens? The attractive influence, or I would say the force of attraction between nucleus and electron is less in D2 here. So if this attraction is less, it can easily lose this electron. If it can easily lose this electron, that means its ionization energy is less. Okay. If ionization energy is less, that means this metallic character is very, very high. In other words, there are some metals which are having very low ionization energy, like cesium. Cesium does have very low ionization energy. Let me tell you for your information, cesium is most metallic element. Cesium is most metallic element in your periodic table. It is having the lowest ionization energy. It is having the lowest ionization energy in whole periodic table. Why? Because it is very large in size. It is very, very, very large in size, because of which it has the highest metallic character. Okay, and that is Why it is having highest metallic character? Because it can lose the electron very easily. If it can lose the electron very easily, that means it can form the cation very easily. If it can form a cation very easily, that means it will have a highest metallic character. Okay, so all of these are connected. So cesium having a very high size, because of which its ionization energy is low. Cesium can show photoelectric effect even in a visible light. Visible light means what? The light you are seeing around you. The light you are seeing around you is what? Whatever part of light or whatever part of radiation that you can see. For example, colors. White light, black light, violet light, indigo light, blue light, yellow light, orange, red, yellow. You can see all of this color. And these colors, nothing but means what? Light. So that you can see. So that part of radiation is called as visible part of the spectrum. We already had seen the large part of spectrum. Remember cosmic rays. Then what do we have after cosmic rays? Cosmic rays. Then you have a microwaves, X-rays, ultraviolet, then visible, then IR, and then radio waves. Right? Cosmic rays are having highest energy. Radio waves are having lowest energy. As far as metals are showing photoelectric effect is concerned, metals generally show photoelectric effect only when they are irradiated with ultraviolet radiation. Ultraviolet radiation is having higher energy than the visible. Okay, but cesium is such metal which has very low ionization energy, then because of which it can show this photoelectric effect even under the action of visible light. Okay, that is very interesting factor. No element can show such thing. No element can show such thing. Only cesium can show photoelectric effect even in a visible light. Okay, but apart from cesium, Kubera Goda, this is JEE section class. Kubera, this is JEE chemistry. We have started the chapter called structure of atom, and we are already into the 9th session of it. Okay, it's a JEE chemistry lecture. So as I was saying, this shows the effect under the action of visible light, but many more metals show it under the action of more energetic ultraviolet light. Other metals which are more energetic, that means in ultraviolet light, then only they can show photoelectric effect. However, cesium can show photoelectric effect even in a visible radiation also. Okay, so moving ahead, I hope you must have understood what is photoelectric effect pretty well. So moving ahead, if you have any doubt, you can ask me in the comment section. Okay, so moving ahead. Now, see, this is the photoelectric. This is your metal. This is your metal. Okay, and one you are seeing here, these are free electrons in a metal. Free electrons in a metal. What is this? This is radiation. This is radiation which is falling on your metal. And what are these? These are ejected photoelectrons. These are ejected photoelectrons. Okay, that is what the photoelectric effect is all about. Whenever this radiation having certain frequency, okay, it is not that you take any radiation, you irradiate metal with that radiation and metal will immediately eject the electrons. No, it will not happen in that way. See, these electrons are under the influence of the attraction. These electrons are under the attractive influence with the nucleus. Okay, so your visible, whatever radiation is falling on the metal, that radiation should have enough energy. That radiation should have enough energy so as to impart it to electron, and electron, by gaining that or by absorbing that much of energy, should be able to overcome. Electrons should be able to overcome the attractive influence and should get ejected. So that's the condition. This radiation should have certain frequency. Okay, this is what just introduction. This, whatever you have seen now, this was just an introduction to the photoelectric effect. Okay. Now let's see photoelectric effect with a much more detail. Okay. So moving ahead. Now, see, this is evacuate tube. You can see here, this is evacuated quartz tube. Okay. This evacuated quartz tube contains two electrodes. You can see here. This is plus, this is minus. Now between anode and cathode, which is plus, which is minus, do you know? Anode, cathode. So an anode, oxidation happens. So oxidation happens on cathode, reduction happens. So oxidation happens, that means system loses the electrons on anode. So anode is positively charged, cathode is negatively charged. Okay, so this evacuated tube contains two electrodes connected to a source of variable voltage. This voltage is variable. Okay, with the metal plate. See, this is the metal plate. You can see here. This is the metal plate whose surface is irradiated as the anode. This is metal plate. So what I was saying, a evacuated tube contains two electrodes connected to a source of variable voltage with the metal plate whose surface is irradiated as the anode. Some of the photoelectrons that emerge from this surface, now have enough energy, to reach the cathode. Some of these have enough energy to reach the cathode despite its negative polarity. And they constitute the measured current. The slower photoelectrons are repelled before they get to the cathode. So this is the instrument where photoelectric effect was actually observed. Okay, but let's not get into much more, details because we don't need it. You only understand what photoelectric effect is, and we will see some of the other factors of it. What were the other factors? See, when the voltage is increased to a certain value, suppose that value is V0 of the order of several volts, no more photoelectrons arrive, as indicated by the current dropping to 0. Okay, this extinction voltage, or it is also called as stopping potential, corresponds to a maximum photoelectronic kinetic energy. That is, EV0 is half mv square. Let's not get this into also. Okay, let's understand this. Electrons come out as soon as the light of sufficient energy strikes the metal surface. This is the metal surface. Okay, light striking here. As soon as light strikes here, electron comes out. Okay, but this light, this radiation, which we shown by h nu, should have certain energy. This h nu, or I would say this radiation, should have certain energy for it to be able to knock the electron from the metal surface. Okay, so that I was saying, electrons come out as soon as the light of sufficient energy strikes the metal surface. Okay, let's see the further part. See, this is the most important part now. You will understand the effect much more detail here. See, the light of any frequency, will not be able to cause the ejection of electron. That is what I was saying. It is not that if you take the metal surface and if you irradiate it with any frequency and the electrons will start coming out of it. No, you should have frequent light of certain frequency. Now obviously, how much frequency your light or your radiation should have, that depends on the nature of the metal. Light of any frequency will not be able to cause ejection of electrons from metal surface. There is minimum frequency. there is minimum frequency called the threshold or critical frequency, which can just cause the ejection. That means your light should have certain minimum frequency. Now you know that energy is directly proportional to nu. Nu is what? Frequency. So correlation factor E is equal to h nu. H is what? Planck's constant, right? So your frequency, your radiation should have certain frequency. That means your radiation should have certain energy, certain minimum energy, okay, so that electron can just undergo ejection. Okay, so there is a minimum frequency called the threshold or critical frequency which can just cause the ejection. So if your frequency is less than that minimum frequency, no ejection will happen. If your radiation has a frequency which is less than a threshold frequency or minimum frequency, then no ejection can happen. If your radiation has a frequency higher than a threshold frequency, then the ejection will happen and the excess energy, then the ejection will happen and excess energy will be imparted to your electron in the form of kinetic energy. You are getting my point? You will understand with much more detail. See, what I was saying, your radiation should have a certain minimum frequency that is called as threshold or critical frequency, so that it can cause the ejection of an electron. Okay, suppose your metal is having electrons very strongly bound to it. Okay, and suppose if it requires around 200 hertz, if it requires 200 hertz of radiation to eject the electrons from the metal surface. Okay, now you are irradiating your metal with some radiation. Suppose that radiation has energy of around 180 hertz. So energy is 180 hertz and the energy that you require to knock or eject the electron is 200 hertz. So even if that radiation strikes the metal, no ejection will happen. That means no photoelectric effect would occur. Okay, now you irradiate your metal with another radiation. Now you have energy of 200 hertz. Now your energy is 200 hertz. The required energy for you to eject the electron is also 200 hertz. So it will strike the metal surface and it will eject the electrons. So photoelectric effect will just happen now. You're getting my point. Photoelectric effect will just happen. Now the third case. You're irradiating your metal with the frequency, with the radiation having frequency around 300 hertz, right? 300 hertz. And your metal requires energy of 200 hertz. Now that 300 hertz while the radiation will strike the metal surface, it will eject the electron. But for ejection of your electron, how much energy required? Energy you require is 200 hertz. And you are providing it 300 hertz, right? So you are providing 100 hertz extra. You are getting my point. You are providing 100 hertz extra. So those 100 hertz will be absorbed by your electron and electron will absorb that energy and will move with some velocity. And that 100 hertz will be imparted to your electron. So it will have some kinetic energy. Okay. Did you understand it with a much more detail now? I hope you must have understood it. Let's see. Let's move ahead. So as I was saying, every metal has a different attractive influence, right? Because the valence shell of every metal is, see, the distance between the valence shell and nucleus for every metal is different. If that distance is different, obviously the attractive influence between the electron and nucleus is also different. If that is different, obviously every metal will require a different frequency to eject the electrons from its surface for it to show photoelectric effect, right? So I was saying this frequency, which frequency? Threshold frequency or critical frequency. This frequency varies with the nature of the metal. This frequency varies with the nature of the metal. Higher the frequency of the light, more energy the photoelectrons would have. As I was saying, suppose this is your metal, these are the electrons, okay, and the energy or the frequency that it requires is 200 hertz. Okay, firstly you are irradiating this with the radiation having 300 hertz, right? So electrons will now get ejected from here. The out of 300, 200 hertz will be absorbed and the other 100 hertz will be imparted to the electrons. So if this is 300, your electrons will have 100 hertz energy. Suppose if I am irradiating your metal with a 500 hertz, then what will happen? Out of 500, 200 hertz will be utilized for ejection and the other 300 hertz will be utilized by electron to show kinetic energy. So you are getting my point. Higher the frequency, more energy your photoelectrons would have. Blue light results faster electrons than red light. Why? Why does it so? Can anyone tell me? See, do you know the VBR pattern? VIBGYOR. What is this? What is it? What do we call this? हिंदी में उसको बोलते हैं इंद्रधनुष. इंग्लिश में क्या बोलते हैं? Rainbow. Remember? Rainbow. So in rainbow, your violet has the highest energy. Violet has the highest energy. Energy is decreasing from violet to indigo, indigo to blue, blue to green. So you can see here, blue has higher energy than red. Blue has higher energy than red. We have already seen this visible light spectrum. Okay, we had seen it the earlier sessions. So blue light has higher energy than red. So obviously, if the blue light has higher energy than red, it will definitely have a higher frequency than red. So if it has a higher frequency or higher energy than red, obviously it will cause your photoelectrons to have a higher energy. Remember? Understood? And that is why blue light results in a faster electrons than red light. In fact, violet will have the fastest electron and red will have the slowest electrons here. Okay, so moving ahead. See, photoelectric current. Now, what is mean by photoelectric current? First of all, do you know what is mean by current? Current is something which is caused by movement of electron. Now, what is happening here? Electrons are getting ejected. So if we made those electrons to pass through an external circuit, it will cause a current, right? So more the electrons, more will be current. Now, since that current is obtained by the electrons, which electrons? Photoelectrons. And that is why the current obtained by photoelectrons is called as photoelectric current. Getting my point? So this photoelectric current is increased with the increase in intensity of light. If you increase the intensity of light, the photoelectric current will also increase. Now, what is the intensity? See, what is the relationship between intensity and frequency? There is no relationship as such. But intensity, your intensity of your light is directly proportional to the square of A. What is A? A is called as amplitude. A is called as amplitude. And what is amplitude? Amplitude is equal to height of crest or depth of trough. Remember, these are your waves. So this distance is called as A. A is called amplitude. So intensity of your light is directly proportional to the square of your amplitude. So what I was saying, the current obtained by this photoelectron is called as photoelectric current. That photoelectric current will increase if the increase of intensity of light is there. That means if you increase the intensity of light, the photoelectric current will also increase. Okay, but both of them are having same frequency. If you take two radiation, one radiation having 100 hertz energy, another radiation is also having 100 hertz of energy. Now frequency is constant. Frequency is constant. Now if you have one radiation with the more intensity of light than the other, then the radiation with the more intensity of light will cause more photoelectric current. But remember, the number of electrons will not increase. The number of electrons will always remain same. only the current caused by those electrons will increase when you increase the intensity of light. Okay. In other words, as I was saying, photoelectric current is increased with the increased intensity of light of same frequency if emission is permitted. If with that much frequency emission is happening, then when you increase the intensity of light, the photoelectric current will also increase. Okay. That means, what is the meaning of that? A bright light has more intensity, as we all know, right? So bright light yields more photoelectrons than a dim. A bright light yields a more photoelectrons than a dim of the same frequency. But the electron energies, remains same. So if you increase the intensity of light, now understand what I'm trying to say. See, whenever the photoelectric effect happens, electrons gets ejected. Those ejected electrons are called as photoelectrons. And if you pass those photoelectrons through an external circuit, you will get a current. So since the current is obtained by photoelectrons, it is called as photoelectric current. Now if you have taken a bright light with some frequency, now you have that much frequency with which ejection can occur. That means photoelectric effect can occur, and your electrons would also have some kinetic energy. Okay, so that is, you have already made sure. Now you are doing what? Now you are increasing the intensity of light. So now when you are increasing the intensity of light, what is happening? The more number of electrons are getting ejected now. Why? Because you are irradiating your metal with a bright light. So when you are irradiating your metal with a bright light, intensity is obviously getting increased. With the intensity, number of electrons getting ejected also increases. When number of electrons increases, the photoelectric current also increases. Getting my point? But the energy with which those electrons are moving is constant. It is not changing. Why? Because you have taken frequency same. Remember, frequency is constant. See, frequency and energy are directly correlated. Energy is directly proportional to frequency. So if you are taken two radiation with the different intensity but the same frequency, then the radiation with a higher intensity will eject more number of electrons, and the radiation with a dim light will eject less electrons. But those less electrons and those more electrons would have same amount of energy, because frequency was constant in both cases. Only their number will be different. You're getting my point? I hope this must have been pretty clear to you. Okay, let me summarize it once again. Okay, see, for photoelectric effect to happen, every metal should be irradiated with the radiation which has some minimum frequency, is called as threshold frequency, which is the characteristic property of a particular metal. Different metals have a different threshold frequency. Okay, if the frequency of irradiation is higher, then the ejected electrons will have a higher energy, and they will be moving with a more kinetic energy. In other words, the frequency with a more energy will eject the electrons with a more energy. Secondly, if you keep the frequency constant, if you are increasing the intensity, the more number of photoelectrons will be ejected. But even if the more number of electrons will be ejected, their energy will always be same, since frequency is same. Energy of photoelectron can only be increased or decreased if you change the frequency. Okay, so that's it for this section. I hope this must have been pretty much clear to you. Okay, sure. Moving ahead with this. Now, the next part. See, light must have stream of energy particle. As we all know, quanta of energy. Remember, the light is getting irradiated into h nu form. What is h nu? Quanta of energy, right? E is equal to n h nu. What is n? Number of quanta. Remember, n is equal to number of quanta. We had already seen in a theory called, which theory? Planck's quantum theory. Okay, So we already know light must have a stream of energy particles or quantum of energy, which is equal to h nu, right? Which I already shown you in the first slide. Suppose the threshold frequency of light required for ejecting the electrons, the threshold frequency of light for required for ejecting the electrons from a metal is nu zero. So when a photon of light of this frequency, which frequency? Nu zero. So when a photon of light of this frequency strikes a metal, it imparts its entire energy to the electron. That means, look at this. See, this is your metal. Okay. This is your metal. And this is where electrons are. Okay. Suppose the energy required for this to happen, a frequency required for ejection to happen is nu zero. It is nu zero. Okay. And this is the radiation falling on it. This is the radiation. So your electrons are ejecting. Okay. And this radiation is having frequency nu. Suppose now if this nu is equal to nu zero, if this nu is equal to nu zero, then ejection will just happen. If this happen, ejection, or I would say just ejection happen. Just ejection will happen. But electron will have no kinetic energy. Why? Because nu is equal to h nu. Sorry, nu is equal to nu zero. Nu is what? Frequency. Frequency is equal to what? Energy. Let's suppose it has energy h nu. H is constant, right? H is constant. H will be associated with the nu also. It will be associated with the h nu also. So h nu is what? H nu is equal to energy of what? Energy of radiation, right? Because nu is the frequency, then h nu is the energy, and h nu zero is what? Is the work function. Is the work function, or I would rather call it as the work potential. So basically what I am saying here, your radiation should have energy. Radiation should have energy is equal to h nu zero, so as it to cause ejection. Okay, and the energy that we are providing is how much? H nu. So as I was saying here, look at here, this is the first case. See here, your E is equal to h nu. So this, in this first case, your nu is equal to nu zero. That means radiation which is falling on metal surface has same frequency as the metal requires. Okay. Otherwise, H is already constant. H is same in both the cases. So when that is the case, that means h nu is equal to h nu zero. When that happens, your kinetic energy will be zero. So your electrons will just get ejected from the surface, but they will not go anywhere. Why? Because they're not having any energy at all. Okay. But if the irradiation, if whatever radiation you are falling here, that means E, this h nu is equal to what? E. Okay. It is having higher energy than h nu zero. It is having higher energy than h nu zero. Then what will happen? Whatever part that it requires to cause the ejection will happen, and the other part of energy which is extra will impart that part of the energy will be imparted to electron in the form of kinetic energy. In other words, the kinetic energy of your photoelectrons will be equal to h nu minus h nu zero, where h nu is the energy of a radiation which is falling on a metal surface. H nu zero is what? H nu zero is the work potential, which is the characteristic property of every metal. Every metal has a different work potential, depends on its attractive influence. You're getting my point now? I hope this must have been pretty much clear to you. That is what the point I was saying here. Suppose the threshold frequency of light required for ejecting electrons from a metal is V0. When a photon of light of this frequency strikes the metal, it imparts its entire energy h nu 0 to the electron. And in that case, kinetic energy is 0. If the radiation which is falling on a metal surface having higher energy than h nu 0, then the whatever part that is subtracting from h nu will be imparted to electron in the form of kinetic energy. And that is why kinetic energy of an ejected electron will be equal to h nu minus h nu 0. Isn't it? I hope this must have been pretty much clear to you. If you have understood it, please like this video, comment on it. You can ask me if you have any doubt. Okay. So moving ahead. So I was saying this energy enables the electron to break away from the atom by overcoming the attractive influence of the nucleus. As you all know, every electron is under the attractive influence of your nucleus, right? So energy which we are providing in the form of radiation to the metal surface, that energy enables the electron to break away from the atom by overcoming the attractive influence of the nucleus. So thus, as we all know, each photon can eject one electron. Each photon can eject one electron if the frequency of light is less than nu 0. If the frequency of light is less than nu 0, then there is no ejection of electron. That means, see, nu is the frequency of ejected radiation and nu 0 is the frequency that is required for ejection to happen. If nu is less than nu 0, no photoelectric effect will happen. That is obvious. No photoelectric effect will occur. Photoelectric effect will only occur if nu is greater than nu 0 or if nu is just equal to nu 0. But when nu is just equal to nu 0, then kinetic energy will be equal to 0. Here, if nu is greater than nu 0, we had seen that then kinetic energy will be greater than 0. Isn't it? Because kinetic energy is equal to h nu minus h nu 0. Right? In other words, see, kinetic energy is equal to h nu minus h nu 0. Right? So h is constant into bracket nu minus nu 0. Right? So nu minus nu 0. Nu minus, if nu and nu minus 0 are 0, then h into 0 is 0. Therefore, kinetic energy is also 0. Remember? See. So if the frequency of light is less than nu 0, there is no ejection of an electron. Okay. If the frequency of light is higher than nu 0, that is nu. I already told you all of this, right? Suppose the frequency of light which is irradiating has frequency nu 0. So nu only. If that nu is higher than nu 0, then photon of this light having higher energy h nu will impart some energy to the electron that is needed to remove it away from the atom, and the excess energy would give a certain velocity, that is kinetic energy, to the electron. In other words, a kinetic energy of an electron is equal to h nu minus h nu 0. Okay, I hope this must have been pretty much clear to you. If yes, please like this video. If you have any doubt, you can ask me in the comment section. Okay, so moving ahead with this. See, as I was saying, kinetic energy is equal to h nu minus h nu 0. So you can also say your h nu is equal to h nu 0 plus kinetic energy. So if h nu is equal to h nu 0, then kinetic energy would be 0. Okay. But if h nu is greater than h nu 0, then the excess part will be imparted in the form of kinetic energy. As we know, kinetic energy is equal to h nu minus h nu 0. So you can mathematically write it, right? Therefore, h nu is equal to h nu 0 plus kinetic energy, isn't it? That is what I was saying here. H nu is equal to h nu 0 plus kinetic energy. And we all know, we had studied in 8 or 9 standard that kinetic energy is equal to half mv square. Remember? Kinetic energy is equal to half mv square. And potential energy is equal to h dg or mgh. Okay, but that's a different thing. We don't need to concern that here. So your h nu is equal to h nu 0 plus half mv square, or you can also say half mv square, which is equal to kinetic energy, is equal to h nu minus h nu 0. Your h nu is also indicated as phi. Okay, how do you read it? Phi. Phi means what? Work function. It is called as work function, or it is also called as work potential. It is a characteristic property of every metal. Nudu Mulu Aditya, you were saying something? Okay, anyways. So half mv square is equal to h nu minus h nu 0. It is also, this h nu 0 is also equal to phi. Phi is also called as work function or work potential. Okay. So I hope this must have been pretty much clear to you. Moving ahead. As I was saying here, your h nu 0, h nu 0 is a threshold energy, right? Or a work function, as I was saying. H nu 0 is a threshold energy or work function denoted by phi. This is what? This is phi. Okay. H nu 0 is a minimum energy of a photon to liberate electron. Okay. Now, see, it's a constant, as I was saying earlier. It is a constant for a particular metal. Every metal has different value of phi. It is a constant of particular metal and is also equal to the ionization potential of gaseous atom. Basically, your h nu 0 of metal is also equal to ionization energy if metal is in gaseous phase. Okay, so let me tell you one more thing. You can see here the graph. You can see a graph. Kinetic energy of photoelectron has plotted against the nu. So we all know the equation. Kinetic energy is equal to h nu minus h nu 0, right? So your kinetic energy is on the y-axis, nu is on the x-axis, right? Do you know the equation y is equal to mx plus c plus minus c? Remember this equation? In this particular case, here y is not equal to mx plus c. Here, your y is equal to mx minus c. So you can see here kinetic energy which is equal to y, nu which is equal to x. So m is what? M is your slope. M is your slope. So this slope is equal to h. You can see here. See, m is equal to h. It is equal to slope, and this is what? This is intercept. This is intercept. If you know the straight line equation, your intercept is equal to c, and it is equal to h nu 0. So if you plot the kinetic energy of photoelectron, your name is Kalki. Which subject? This is chemistry, Rupesh. This is JEE chemistry on a practically live. Okay. So if you plot the kinetic energy of photoelectron against the nu, what is nu here? Nu is the frequency of a radiation. Nu is the frequency of a radiation. Okay. So kinetic energy of photoelectron, if it is plotted against the nu of a radiation, then you get a straight line. In that straight line, slope m is equal to h, and the intercept, which is equal to C, is equal to h nu 0. H nu 0 is equal to what? Phi. Work potential, remember, h nu 0 is also equal to phi. It is also called as work function or work potential. In other words, if you get this graph, the intercept of this graph is equal to work potential of that given material. Okay, see, you need to understand this point pretty well. Kalki sir, me, that is my father name. Yeah, that's okay, Kalki. I got it. No problem with that. Which standard are you, by the way? Are you in a 11, 12 standard or you're 8, 9, 10 student? Because this is for 11, 12 students. Okay. But yeah. So I was saying intercept of this straight line is equal to work potential. Okay. So that is what I have written here. The kinetic energy of the photoelectrons. The kinetic energy of the photoelectron increases linearly with the frequency of incident light. As I was saying there, energy of your photoelectron is directly proportional to the kinetic energy of photoelectron. Basically, whatever radiation you are having, if you increases the frequency of your radiation, then only the energy of photoelectron can increase. If you increase the intensity, the number of electrons ejected will increase, but the energy of those electrons would never ever increase. Okay? So the kinetic energy of photoelectron increases linearly with the frequency of incident light. Thus, if the energy of the ejected electron is plotted, as a function of frequency, it results in a straight line. See, this straight line indicates what? That kinetic energy of your ejected photoelectron is directly proportional to the frequency of your radiation. That was why you got a straight line, right? Otherwise, you won't have got this straight line. So it gave us a straight line whose slope is equal to h. H is what? Planck's constant, right? And intercept is equal to h nu 0, which is also called as phi, work function or work potential. Okay, I hope you must have got it very well. If you have understood it very well, please like this video. If you have any doubt, you can ask me in a comment section. Okay, so moving ahead. The next part is types of nodes. Now, first of all, you need to understand what is mean by node. See, do you understand the orbitals? See, orbital is that part of the radiation, not radiation actually. Orbital is that part of the atom where probability to find the electron density is maximum. Orbital is that part of an atom where probability to find the electron density is maximum. And what is node? Node is that part of the atom where probability to find the electron density is 0. In nodal part, you will not find any electron density. So it is just like, just consider your home. In which part of your home do you spend your time maximum with? You might be spending your more time in a living room, or maybe on a desk in your bedroom, okay, or maybe playing somewhere in your house. So that part where you spend your maximum time is your orbital. Suppose if you're an electron, then that part will be your orbital. Okay, and if you consider a kitchen, if you consider a kitchen where your mother works, right? If your mother cooks food for you, you never go to kitchen, right? You never go to kitchen. So kitchen will be a node for you. If you are an electron, kitchen will be a node for you. So in other words, node is that part of the atom where no electron density is found. Okay. So I was saying the points at which probability of finding an electron is 0 is called as radial node. Now number of radial nodes is equal to n minus L minus 1. N minus L minus 1. What is n? Remember principal quantum number? Your n is principal quantum number. N is principal quantum number. What is L? L is azimuthal quantum number. We had seen all of this in the last lecture, remember? Your L is azimuthal quantum number, your N is principal quantum number. So number of radial nodes shown by any species is equal to N minus L minus 1. Okay. We will solve a small question on that. Okay. But before moving that, let me tell you something. See this part, this is your nucleus. This is your nucleus. Okay. Now, see what are they saying? Electrons cannot be present at 2a0 distance from the nucleus. So this distance is 2a0. You can see here 2a0, 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 2a0. So your electrons cannot be present. Electrons cannot be present at 2a0 distance from the nucleus. If we join all the 2a0 points, by the way, these 2a0 terms and other terms have been found from the quantum chemistry. Okay, we don't need to involve ourselves much with the quantum chemistry. Just need to understand what is the summary of it, and I'm making you understand what is summary of it. Okay, so if we join all of these 2 0 points, what do we get? You get a sphere here, right? You are getting sphere. This is sphere, right? So in this spherical part, electron cannot be present. That is why this radial node is also called as the spherical node. See, if we join all the 2 0 points to form a sphere, we can see that electrons cannot be present on a surface of a sphere. Electrons cannot be present on a surface of a sphere. However, it may be present inside the sphere or outside the sphere. Your electrons may be present inside the sphere or outside the sphere, but it cannot be present on the surface of the sphere. Okay. So at 2a0 distance, probability of presence of electron is 0. At 2a0 distance, probability of presence of electron is 0. And since the sphere is formed, these radial nodes are also called as spherical nodes. The radial nodes are also called as spherical nodes because in the spherical part, electrons cannot be present. That is why radial nodes is also called as spherical nodes. Okay, remember this always. Now, your radial nodes are spherical in shape. The radial nodes are spherical in shape. That is why they are also known as spherical nodes or a nodal sphere. Okay. Now let's calculate the radial nodes or spherical nodes for some species. Firstly, let's take for the 1s orbital. How many nodes it has? For 1s orbital, n minus L minus 1. What is 1? N is 1. What is L? L is 0 for the s orbital, right? So 1 minus 0 minus 1. 1 minus 1, 0. So your 1s orbital do not have any node. Let's take 2s orbital. 2s orbital, again formula. What is the formula? N minus L minus 1. N is 2, right? N is 2. L is 0 minus 2 minus 0 minus 1. 2 minus 1 is equal to 1. So your 2s orbital has one node. Then 3s. Again, N minus L minus 1. N is 3. L is 0. 3 minus 1 is equal to 2. So 3s has 2 nodes. Similarly, 4s will have 3 nodes. 5s will have 4 nodes and so on. That's how you can calculate the radial nodes for the s orbit. Let's calculate for the p orbit. Now p orbital starts from 2p, right? There is no 1p. So 2p, n minus L minus 1. What is n? N is 2. What is L? L is 1 for the p orbital. Remember? SPDF. Values of L as 0, 1, 2, 3. SPDF. So L is 1. 2 minus 1, 1. 1 minus 1, 0. So 2p has no orbital. Sorry, 2p has no node. Sometimes there is a slip of tongue. Please understand. I mean to mean a node here. Okay, radial node. Then you have a 3p. So for 3p, again n minus L minus 1. What is n? N is 3. What is L? L is 1. 3 minus 1, 2. 2 minus 1, 1. So 3p will have a 1 node. Then 4p. 4p, n is what? N is 4. L is again 1. 4 minus 1, 3. 3 minus 1, 2. So it will have 2 nodes. And so on. That is how you can calculate the number of radial nodes. Remember, there has been question asked so many times about radial nodes in exam. Okay. When we will solve the question based on this, then you will understand it. Okay. So moving ahead. The energy comparison. See, for energy comparison, for all the atom, we use the above rule. Remember? Above rule, 1s, 2s, 2p, 3s, 3p. You can use this, or we can use the n plus L rule. Remember? We had seen all of this in the last session. Okay. So for energy comparison, above rule should be used. But for hydrogen atom, subshell belonging to particular shell, possesses equal energy. For hydrogen, one s orbital has a lesser energy, okay, but hydrogen has only one electron. Remember, atomic number of hydrogen is 1. So this is nucleus surrounded by just one electron. Okay, but it might have some other shells, but those shells will not have any electron. So that is why the 2s will be equal to 2p. If the n is same, energy will also be same. Similarly, 3s, 3p, 3d, all of them will have same energy. The same thing will not happen with the other atoms. For the other atoms, if you consider the other atom, 3s will have the lowest energy, then 3p, then 3d. Similarly, 2s will have a lesser energy than 2p. That is for the other atoms. But for hydrogen, it is like this. Okay. So that was the note I wanted to tell you. There might be question asked on this in a JEE exam. Okay. So obviously we are preparing for it. So you should know these small things. Okay. So moving ahead. Now angular function. See, what is this angular function? It is basically nothing but the angular node. We had seen the radial nodes. Now we're going to see the angular nodes. What does it do? It gives us an idea about the shape, orientation of the orbital. It gives us the idea about the shape and the orientation of an orbital. Do you remember? The values of m changes from minus L to plus L. If your L is equal to 1, your m will have values minus 1, 0, plus 1. And if the L is 1, orbital is p. That is why p orbital has these three p suborbital. But the values of them like minus 1, 0, and plus. Okay. That was why your p exists in 3 orbitals, minus 1, 0, plus 1, or you can name them as px, py, and px, py, and pz. So this is your px. Why I'm saying this is px? See, this is x orbital. This is your x orbital. This is your y orbital. So when it is along the x-axis, it is px. You can see here. This is along the x-axis, so px. This is along the y-axis, so py. And third one is what? This is your z-axis. So if this is along the z-axis, it's a pz. Pz. Along the y-axis, py. Along the x-axis, px. Okay. So that is what a p orbital. That is how p orbital actually exists. Okay. Now, see, for s orbital, angular part is independent of theta. Angular part is independent of theta and phi. So there would be 0 angular nodes for s. S orbital cannot have any angular node. For s orbital, you can have a radial node. For s orbital, you can have a radial node. But for s orbital, you do not have any angular nodes. because it is independent of theta. Okay, so technically number of angular nodes for any orbital is equal to L, is equal to L. So you take any p orbital, you take any p orbital, any p orbital, by that I mean what? You can take 2p, 3p, 4p, 5p, 6p, 7p. For all of them, angular node is equal to L, and L is equal to 1 for p orbital. Remember? So every p orbital, you can take 2p, 3p, 4p, 5p, 6p, 7p. For all of them, angular node is equal to 1. However, their radial nodes will differ. Why? Because the formula for radial nodes is n minus L minus 1. So formula of radial node has value of n. And as the value of n changes from 2p, 3p, 4p, 5p, the number of radial nodes will also change. Okay. But for angular node, L will be constant. Okay. So moving ahead. See, let's see here. For px, how do you write a px? These are the three directions. This one direction, this another direction, and this is z direction. Remember? So this is your x, this is your y, your z. Now your orbital is present here. See, this is where your orbital is present. I would rather write electrons there. So this is where you have electrons, right? This is where you have electrons. And the plane, which is plane? See, plane is formed by, your plane is formed by two direction. Plane is formed by two direction, any two direction. So here electrons are present in x. So your zy, see, this is forming a plane now. You can see here, this is the plane, and this plane is perpendicular. See, here you are already seeing in 3 dimension. This is 3 dimension. Here I am telling you in the form of drawing. I am drawing live in front of you, so that you will understood this in a better way. Okay, so this is the plane passing through your x. See, Jessica Victoria, you said something, message got retracted. But anyways, so this is a plane. Now you can see this plane is present in YZ plane. See here, this is the YZ plane, and in this YZ plane there is no electron density. There is no electron density. Why? Because electron density is present in an x orbital. I would say in an x direction. Your electron density is present in a x direction. So since your electron density is present in a x direction, you do not have any electron density in the YZ plane. YZ plane is passing through your x direction. In x direction, electron density is concentrated. And that is why this is called as orbital. That is your orbital. Which orbital? Px orbital. And in the YZ plane, you do not have any electron density. That is why that is called as a nodal plane. It's your nodal plane. Since it's present in a YZ direction, it is called as YZ plane. Okay? So for a px orbital, YZ plane is a angular plane, or I would say angular node, or a nodal plane. So for px, YZ is a nodal plane. For a py, XZ is a nodal plane, and for a PZ, XY is a nodal plane. Got it? I hope you must have understood it. If the orbital is PX, YZ will be nodal plane. If orbital is PY, then there will be no electron density in XZ. So in that case, XZ it will be your nodal plane. If it is a PZ orbital, then there will be no electron density in X and Y direction. In that case, XY will be your nodal plane. Okay. So I hope this must have been pretty much clear to you. Moving ahead with this. Now the last part. DXY. See, DXY is a d orbital. In DXY, electron density is present in the X and Y direction. See, for a p orbital, whenever I am saying px, that means electron density is along the x-axis. When I say py, electron density is along the y-axis. When I said pz, electron density is along the z-axis. But for your d orbital, dxy means electron density is present between the x and y-axis. Whenever I say dyz, electron density is between the y and z axis. Whenever I say dxz, that means electron density is present between x and z axis, and so on. What so on? I told you everything here. So here electron density is present. So if I take xy, if I take dxy, this is dxy, right? This is your dxy. Then your nodal plane will be xz and yz. If I take dyz, see there are three options between three axes, xy, yz and xz. So if you take a dxy, nodal plane will be yz and xz. If you take dyz, the nodal plane will be what? Sorry, nodal plane will be dxy and dxz. Sorry, only xz and yz. If you take dxz, the nodal plane will be xy and yz, and so on. Okay, that is how you can find out the nodal planes. It is that easy. It is not that difficult at all. I have told you what it is for the p orbital also and for the d orbital also. Okay, so that's it for today's session. We have covered how the nodes are, what is photoelectric effect, what is the threshold frequency, and all of that. So that's it. On this note, I announce, or I would say, this chapter has been over. Okay, we have considered, we have taken, I have taught you each and every concept from this chapter. The chapter is completely over. In the upcoming session, we will solve the questions, the numericals. We will solve the numericals and the objective question based on this chapter, and we will also solve the PYQ. What is meant by PYQ? Previous year question. Okay, because this chapter is really important for your JEE exam. Okay, that's it for this session. If you really like this video, please like this video, comment on it, subscribe to Practical Live on YouTube. If you want to explore more, you can download our app from Apple Store or from a Play Store. You can log into it. You can check into it. You can check different courses. We have a courses in the robotics, Vedic maths, coding, chess, and very soon we are bringing the course Python for all of you. Okay. So that's it for today's session. Bye bye from my side.